These are critical players in that whole process.
Understanding the musculature and the vascular and nervous systems of modern animals allows him to reconstruct how tissue interacted with bone in the past.
All of a sudden, the fossils look different. All of a sudden, it's not just a random collection of holes and grooves. All of a sudden, conceptually anyways, there are blood vessels and nerves coming through those holes and grooves. And not just any blood vessels and nerves, but nerves and blood vessels that we know and understand.
Though terror birds were aggressive predators, they would have had no chance against this huge herbivore. It lumbered across South America for 2 million years before it mysteriously became extinct. There's something decidedly medieval about Doedicarus. Maybe it's his rhinoceros-like size. 3,000 pounds of flesh supported by feet that are barely visible beneath his bulk, kind of like a moving fortress. Or perhaps it's that chainmail armor, 1,800 bony plates concealing a deep layer of fat that acts like a shock absorber in battle. Or it could be that spiked mace-like tail that can be wielded against other males during mating season. And, of course, against predators.
It was a plant eater, and it was a big Volkswagen-shaped animal that probably was not swift. A pretty amazing defense mechanism, though. Who would want to have him for lunch? They couldn't really take a bite.
It had a huge domed, bony shell. It's completely covered its entire body, especially when it's squatted down on the ground.
Doedicarus was not built for beauty, certainly not for speed, but he was built to last. In fact, he managed to survive for most of the past 2 million years. But like the rest of his sturdy Pleistocene caste, the mammoth, the saber-tooth, and the woolly rhino, he disappeared within the last 11,000 years. Scientists are searching for the cause of these great beasts' disappearance. Why did such hardy creatures, also known as the mammalian megafauna, become extinct? Not surprisingly, the answer isn't simple. It begins with the concept of extinction, which, on the positive side, creates opportunity.
The rise of the mammalian megafauna wouldn't have been possible were it not for the extinction of the dinosaurs. And to examine this idea, it's instructive to think about the idea of niche, a biological niche. You can think of a niche essentially as the job description of an organism. Not just who was it, but what did it eat, who ate it, what was its environment, its behaviors, its physiology, and all of those things together combine to make the niche of an organism.
The dinosaurs had taken all the good jobs during the Cretaceous period. Their extinction made room for new blood.
All of the non-avian dinosaurs go extinct 65 million years ago, and essentially there are all these environmental job descriptions now lying vacant. And this time it's the mammals that step up, go through this burst of evolution and diversification, and then you see mammals occupying niches that were formerly occupied by dinosaurs.
Doedicarus was likely better equipped to handle one-on-one combat than changes in the weather.
When we talk about extinction, we should realize that change is bad. Organisms are evolved specifically for a certain habitat, and anything that changes that habitat's not likely to be good for them. So the first rule of extinction is change, no matter what it is a bad thing.
The so-called Ice Age extinction, lasting from approximately 13,000 to 9,000 years ago, wiped out many different kinds of animals, including Doedicarus, mammoths, saber-toothed cats, and woolly rhinos. Its cause has long been a subject of debate in the scientific community.
Ever since the days of Darwin, when they first started finding these large Ice Age mammals that were clearly no longer around, people have speculated as to why they all went extinct.
There are competing theories. One prominent one, the overkill theory, postulates that the human expansion into more habitats put pressure on other mammal species. The so-called Clovis people moved from Asia into North America, perhaps as early as 14,000 years ago, bringing with them flint spearheads for hunting large game.
Especially in North America, there is a close correspondence between the last radiocarbon dates on the big Ice Age megamammals and the first appearance of humans with Clovis points that came over from the Bering Land Bridge from Asia. And so the overkill school says that all these naive North American large mammals had never had a predator like humans, and that when humans came, they probably wiped them out. But there are certainly problems with the idea that humans wiped out everything. The biggest problem of which is that we don't have evidence that they actually hunted a lot of these animals, and it's very odd that certain animals that they don't seem to have hunted at all died out, and that there's no reason to think they would die out.
Some scientists theorize that climate change, a rapid warming that brought on the mild climate that we have now, disrupted habitats and caused the extinction.
This is also a time of great climatic change. It's the rapid transition from the last glacial to the present interglacial, which we're in right now. And that event took place very rapidly. We're talking about major shifts in just decades.
Scientists believe that climate change can't entirely explain the extinction because there had been other cold and warm snaps during the Pleistocene that didn't lead to mass extinction.
My feeling is that it's probably the case where people like simple answers, but nature isn't so simple.
The most accepted theory now is that there was a combination of climate change and overhunting that brought on mass extinction.
There are certainly climatic stresses going on, and maybe humans are just like the tip of the iceberg, or they pick on certain animals, especially like mammoths and bison, and might have pushed some of those, like mammoths, to extinction.
When you talk about theories of extinction, they're not necessarily mutually exclusive. Extinction may be severe because 2 or 3 of these factors came into play at the same time.
Extinction, though it often wipes out creatures that survived and adapted for millions of years, is a partner to evolution.
Evolution doesn't actually produce the best possible solution. It only produces a better solution. And if, in fact, we didn't have extinctions, probably what would happen is that evolution would pretty much grind to a halt.
And so we might find ourselves in a similar ecosystem that was around in, for example, the Jurassic, and we might be living in the shadow of dinosaurs.
It's only extinctions that give an opportunity to roll the evolutionary dice one more time. As a result of this, we might get something new and perhaps even better than we had before.
Scientists are continually confronted with the bones of bizarre creatures. How do they approach something they haven't seen before? Most often, paleontologists dig up the bones of a partial skeleton. The rest of the remains have been eaten by predators, scattered by a shifting geology, or simply eroded from exposure. These partial remains present basic questions about the creature. Why was it designed in this way? What behavior can be inferred about the beast that wore these bones? Paleontologists are faced with these challenges every day. But how does this work in practice? What are the first things a scientist does when faced with a set of mysterious, anonymous bones?
Presented with an animal like this, it's a really good question is to see if we can figure out what kind of animal it was, how it lived its life. Certainly it's a very interesting sort of animal. Looking at the structure of the teeth is one of the first things we can do to see what an animal was like and what it did. One thing that's remarkable about these teeth is these are the teeth of a predator. Not only are they sort of sharp and pointy, but a key feature is that they're actually directed backwards. So we call that recurved. It's actually very similar to what we see in the teeth on the skull of Velociraptor right here. What that means, if you're a prey item, is that it's pretty easy to get in, but it's pretty tough to get out. Another attribute that we can see by looking at this is this animal had really big jaw muscles. This whole cavity in here is absolutely enormous for a skull of this size, and all of these muscles sat right down in here. What that suggests is that whatever it was biting, whatever prey organism, it was actually biting it very hard.
This skull looks like a reptile to me, but it's not a dinosaur. Dinosaurs had a particular hole in the skull between the eye socket, which is here, and the nasal openings here. It is a reptile, but it's not a dinosaur.
A really interesting thing actually relates to this structure right here in the nose. This is a very unusual kind of structure that is actually related to sort of a funny kind of sense of smell, in that it's sensing chemicals. This is actually something that we call a vomeronasal organ, and it's not regular smell. Regular smell is actually very far back in the nasal cavity. This is actually a special kind of organ that's involved with actually tasting smells. Seeing this in this animal right here tells me that this animal probably, almost certainly, had a forked tongue.
So I'm going to take this skull and try to flesh it out. Try to put some flesh on the bones and do my recreation of whatever this creature must have looked like. I can see a big eye socket there. He looks like he had fairly large eyes. Give him a nice sort of reptilian slit pupil look there. Straight mouth. He has sort of a curving lower jaw. Give him a sort of a reptilian sort of dewlap down there.
There are some other features here. For example, on the lower jaw, this is actually a hinge. And this animal can flex its lower jaw downward as it opens its mouth, which allows it to stretch and bend the lower jaw down. This is a feature unique to just a few families of lizards.
But there's little speculation left for Dr. Whitmer. The nose structure leads to a positive identification.
This is not an iguana. This is not a gecko. This is a monitor lizard, because this is a very specialized kind of nose structure that we find really only in monitor lizards. From there, the next question is what kind of monitor lizard is it? There's lots and lots of different kinds. Based on the size of this, I would suggest it's almost certainly a Komodo dragon, which is the largest living lizard today.
A monster from the present. A Komodo dragon weighs in at around 150 to 300 pounds. They are the top predators on the Komodo Islands in Indonesia.
They hunt fairly large mammals, and their way of hunting is to jump out on a game trail and quickly put a bite on a prey. They have in their saliva Clostridium bacteria, which are toxic. So even if it only gets a nip on the animal and the animal gets away, it's infected the wound with a bacterium that will kill the animal in 2 or 3 days.
They can ingest up to 80% of their body weight in one meal. Komodo dragons may swallow smaller prey whole. Their ancestors are ancient and can be traced back to about 100 million years ago in Central Asia. We can explore both their lineage and behavior by taking a closer look at their brains.
Certainly, one of the key things that we need to do and try to sort out how this animal lived its life is actually run this thing through a CT scanner so we can see inside, get back to this area, the brain cavity, and see what kind of structures that we might be able to see. Okay, this will be interesting. This is actually the skull of a Komodo dragon. So it's not a dinosaur, but it's still really interesting for us to look at, partly because it's the largest living lizard. Let's give it a go.
The scan reveals modest-sized cerebral hemispheres, indicating an animal that lives by instinct. The inner ear, more advanced than that of its ancestors, suggests enhanced hearing and balance, key for a pursuit predator. Though fearsome, the Komodo looks modest compared to our monsters from the past. They may seem particularly spectacular and freakish from our present moment, but it's mostly a question of perspective.
I think there's a perception that animals of the past are somehow more extreme than animals alive today. But I think what you have to keep in mind is that today we're looking at just a single interval in geological history, just an instant, literally. When we look at the fossil record, you're seeing, in the case of hard-bodied life, you're seeing 500 million years of evolution. So that's a lot of time with which to work, and over geological time, very, very improbable events can become probable. The if you look at 500 million years of evolution,